So we have time for discussion now, and I'd like to open it up. We had a number of really good talks in this session that open up some good questions. I'd like to sort of turn back to something that Steve raised a little bit ago, and that's the James Webb Space Telescope and synergy between James Webb and arrays on the moon. Last couple of days, I've had a lot of people come up to me and ask about the results from James Webb, those beautiful images. And last night we showed at the planetarium several of those images and talked about them. But there's some confusion about what Webb can do, in part because of some of the PR that's gone out there. And the impression a lot of people have is that James Webb is going to do truly the first stars. And I've even had people come to me and say, well, why are you doing these radio telescopes on the moon? Because isn't James Webb going to do the dark ages as well? And I point out to them, there's nothing for James Webb to see in the dark ages. There's no signal there, but there's some confusion. So we've got some work to do there in just clarifying. But importantly, there is real synergy between the Webb results and what we're going to do with the arrays. And so Steve and David, I was wondering if both of you might talk a little bit more about what that synergy may look like. How would we go about combining some of these databases together?
I think there are several ways to do that. First, I will quickly show quantifying how difficult it will be for JWST to get out this way. So this is a plot that uses the models of galaxies that I showed before and predicts how much of the starlight you can see given a survey. So the x-axis here is the magnitude limit of the survey you're doing, which so the left are the deepest surveys. And then the y-axis is the fraction of star formation that you would see above that limiting magnitude. So the second dashed line here, vertical line here with the arrow, that is the deepest planned survey by JWST so far. And at redshift of 12, according to these models, you're only getting about 10% of the star formation. At redshift of 15, it's a couple percent. And we think the first star, this redshift is astronomer speak for time, but the first star is probably formed around a redshift of 30, all right? So we're not getting anywhere close to that era with direct JWST observations. Now, there are some things you can do quasi-directly. So the supernovae of these first stars may be so extraordinarily bright that you can see them with these surveys. Similarly with gamma ray bursts. So as these stars end their lives, we may see them, but we're only going to see, you know, a small fraction of the actual events that are out there. I think what will be most powerful will actually be JWST is going to do a great job of pinning down that normal galaxy population because it's going to push it to earlier times and to fainter magnitudes than we can do now by a huge amount. I mean, it is a huge improvement. And so it sort of gets that part really well known. And then if you get the 21 centimeter to do the whole thing together, you can subtract two things you know pretty well, and you learn a lot about what's in the middle. So that's, I think, what is most exciting is kind of setting the big stuff very well, and then we can figure out what's left over with 21 centimeter.
Yeah, that's a great description. David, do you want to add anything further about other telescopes too that we can combine with our lunar arrays to add information about this early universe epoch?
Well, I was just going to add to what Steve was saying that you can, I wanted just to point to the talk, again, as mentioned before from Joshua in the next session. So where we can combine luminosity functions and already that paper shows some of that already with existing luminosity functions from current surveys. But so we'll be able to add JWST into that and combine that in order to put constraints potentially on models of dark matter beyond the standard cold dark matter, for which is important to know the number of halos and how massive are those halos, essentially. So the combination with the counting of the galaxies, that would be important.
That's great. Nivedita, let me ask you for questions and help me moderate this discussion a little bit further here.
I will. Sorry. Yeah. I did have a question for David, though, for your talk. From your talk. So when you did your simulations for the SVD, generating all the possible scenarios, was it taking into account all possible systematics of Lucy, or was that a general, like actual systematics of Lucy, or is that to be done?
So yeah, so thank you for the question. That's a question. So this is to be done. So now, we in a collaboration to do so. So you need, so the examples that I put are all simulations that we show that we can do that. But then for any specific instruments, you need to know the specifics of that instrument. And again, Lucy still is in development. For example, now there are decisions being made about the antennas, right? So when these decisions are made, and then we can actually use this analysis as well to make decisions in that direction. But so when decisions are made, you'll give us the characteristics of the beam that you need to make the training sets of the beam, right? In addition to that, we'll need information as well from the lunar surface. So we hope to get some of that, some examples from Rosa's, hopefully, although maybe, it will be in a different location. So I don't know how different it will be, but at least it will be informed of how we can do this analysis and which kind of ranges maybe are reasonable. So again, and then again, this is for the beam and for the lunar surface, and then for the receiver itself, we need also to know the details of the receiver in order to actually model the gain and the offset. But yes, the point is that that we can do that for any specific instrument when we have all these details.
Yeah, just to add what Dave was saying, what's exciting is we are going to have our first radio instrument on the moon in just months. Rolls is going to be carried by the Intuitive Machines lander, and may very well be the first of the CLIPS landers, scheduled, I think, at this point for very early in 2023. And that's going to allow us to start exploring these systematics, and specifically on the moon, and being able to fit, in particular, understanding the electromagnetic interaction between the radio antenna, the beam, and the dielectric material, which makes up the subsurface. We need to know that, as David and others have pointed out, because we need to know the radio beam when we start thinking about doing cosmology with Lucy. So we're really anxious to get our hands on some real data, because we've been talking about this. In my case, I've been talking about it for almost 40 years about putting radio telescopes on the moon. So it's exciting to see this happen. Let me throw it open to some questions, Mark. And we've got another microphone in the middle there too.
Yeah. Hi, this is Mark Kleinwald from Radboud University Nijmegen, and I have a couple of questions and also a comment, maybe also on the discussion on what other instruments can we use in extension to what we're doing on the moon. I think we should also realize by the time that if we're lucky, that we have all those instruments on the moon, by that time we'll also have SKA being developed, and that will extend down to very low frequencies, not so far as we can do from the moon, but that's a really nice, especially when you have an overlap between in frequencies between those two systems. This is very good for calibration purposes, I think, but that will also tell us more about this cosmic dawn possibility. So I think that's interesting. And one of the things that I was wondering about is, this was a question maybe to all of you, is if we put an antenna on the moon's surface and we look at the beam, so how do we expect the lunar regolith to influence the performance of the antennas, and how do we deal with reflections from signals that go into the regolith and then come back? That's, I see people laughing. It's a standing discussion.
Only because we recognize that we've been doing a lot of thinking and modeling about this. But Nivedita, you've for part of your dissertation, you did some modeling on this, and maybe we could start off with you responding to that.
Yeah. One of the few things that we saw, first thing to actually notice that when we put the dipole on the regolith, based on how low the conductivity is, most of the beam is actually in the regolith. Right. This is just partly, that's why the gain's really low, but then we have the sky being louder at that point. So it's okay if you have a low gain. But the other problem is the impedance of these antennas at such low frequencies is quite high. And once you add it to the regolith, it's more capacitive also. So that adds more losses in the kind of balance and the receivers we design. So that'll be. The other thing that we looked at was, especially for the cosmology case, we don't want the beam to vary too much with frequencies. Overall, that is not an issue, is what I've simulated. As far as I've simulated that the regolith doesn't have any boulders in it that's reflecting back. But like you said, if there are scattering objects, there's boulders, all of this has to be simulated and looked into. Maybe these can go into the SVD simulation that the boulder group is doing, but these are scenarios we'll have to do and see what's the worst case situation we can tolerate.
Yeah, and in those cases, do you think you need a ground plane? So if you
okay, that's a ground plane would be ideal. We wouldn't be looking at the gain would be perfect, the chromaticity below, but we're talking about 128 pairs of antennas that will be deployed by a rover. So it's convenience versus like, do we have the also the capabilities of having ground planes for so many antennas and racing them? What will you use to race them? That's something left to deploy those.
Yeah.
So,
And I think we've learned the ground planes are not perfect as well.
no,
And they have flaws, and that can introduce systematics as well. But yeah, it's interesting because we too have been putting a lot of effort into doing modeling using the CST package and FICO. And the problem, of course, is we lack data on what the subsurface actually looks like. So one of the things we've done in selecting our landing site for Lucy, and what's nice, since we have our own radio astronomy lander, we can choose the landing site. And so what we've been doing is looking at regions on the far side using the Grail maps on crustal thickness. So we've selected sites that are 25 kilometers and greater in crustal thickness because we really like well-mixed soil. That will minimize the number of reflectors that's there. Still doesn't tell us, about how the dielectric constant changes or the loss tangent, but we can infer some of that. The other thing we're planning to do with Lucy is to map the beam by having a radio beacon in the communication satellite. We're talking with ESA about that. And our radio antenna is on a turntable and it will rotate and allow us to potentially map the beam. Now, having said that, that sounds great, but as we know, mapping the beam down to 30 dB, maybe 40 dB if we're lucky, that would be great, but we really need to get it down to 60 dB. So there's still going to be a lot of uncertainty. But again, that's where the training sets come in that David was talking about. So having a set of models and simulations that we tie together with data that we start collecting from the moon, we have to inch our way towards this.
Yeah, that sounds good. Can I ask another question to David? Maybe I missed that, but in your presentation, you explained that obviously, if you want to distinguish between the foreground emission and the 21 centimeter emission, you're looking at time variability, right? But do you also use the fact that the 21 centimeter emission is coming from all the sky, all around us, and some of that foreground emission is more, coming from one direction? Do you use that already in distinguishing between the signals?
Yeah, thanks. So yes. So, well, I mean, implicitly. So essentially, the foreground, of course, is also full sky, right? But the fact, so basically, actually, this is the key thing of the foreground and how it affects us is because we're interested actually not in a spatial measurement, which will be, for example, for the interferometry, but for the global signal, we're interested in a frequency measurement, right? But the frequency dependence of the space dependency or the angle dependence of the foreground, when combined with the beam, it becomes actually frequency dependent, right? And that we're interested for the global signal. So this actually, by having, again, also training sets or modeling sets from data actually as well for the foreground, that actually help us to know about the angle in the sky and combine that with the beam. And actually, just to add that from your previous question and to add what David and Jack were saying, with the CST and FICO simulations packages, electromagnetic simulations, when we have data, it's going to be very important, again, to do very detailed simulations of different scenarios, of different possible reflections, as you were saying, or possible properties of the foreground. And these simulations are expensive, but when we have the data, will be worth it. And we're thinking as well about doing some kind of emulators and so on. But it will be doing a lot of that.
We're about out of time, but we've got one more question I want to get to from the audience here. Please go ahead.
Sure. This is coming from the rogue geophysicists in the astrophysics section. Following the discussion about the role of regolith in analyzing this data, I just wanted to reiterate the common adage that someone's noise is someone else's data.
Right.
And there's a lot of potential very strong synergies between these concepts and doing things like lunar seismology, which I know that the Farside team considered with doing distributed fiber measurements.
Absolutely.
So it'd be, as you all consider doing this and studying this more, I'd recommend reaching out to the geophysics and geology community, because there might be, say, joint inversions that one could do, looking at the ability to recover where the boulders are, even if they can't tell you their dielectric constants, might be able to tell you the size and distribution. That could be useful for you all.
So. Absolutely, it's an excellent thought, and one that we're already working on as we're rebuilding our NEST team for our next proposal. We're doing exactly what you suggest. So thank you very much. We're out of time, but I want to just thank all of our speakers and all of our discussants. So one more round of applause for everybody.